On this question, we want to classify the given function as polynomial, rational, or root, and then find its domain. We're going to write the domain in interval notation, and the function we're working with is g of x equals square root of 2 minus x. So I think this one is a little bit obvious because it has a radical. It is a root function. So anytime you have a variable underneath the radical, you have a root function. Now when you're finding the domain of this root function, you want to pay attention to whether you have an even index or an odd index. Now this example is a square root, and there's no index. Let me show you where the index usually is. The index is usually right here, just on the outside of the radical. Now this one doesn't have an index, which means that we assume that it is a 2. That's why we call it a square root. So this has an even index. Now that's significant because when you have an even index, for example, if you were to calculate the square root of -1, you get an imaginary number. This is not a real number. And when we're finding domain, we're only concerned about real numbers. So when you have an even root, you do have a restriction. And that restriction is that because the negative numbers result in a complex or imaginary number, you want to exclude them from the domain. So we want what's underneath the radical to be non-negative, or positive or 0. Non-negative means 0 or positive. So in order to find the domain, we're going to create this inequality. This inequality takes whatever's underneath the radical and sets it to be greater than 0, that's positive, or equal to 0, that's 0. So this is a way of including what we want. We want what's underneath the radical to be positive or 0, and excluding what we don't want. We don't want a negative under the radical because that causes imaginary numbers. So to find the domain, we're going to take our expression that's underneath the radical, and we're going to set it greater than or equal to 0. We're going to solve. We're going to subtract 2. We've got negative x is greater than or equal to -2. Divide by -1. And we have x. Because we divided by a negative, we're going to reverse that inequality symbol. We have x is less than or equal to 2. This is our domain. Now on a number line, we would mark a 2 with a closed circle. I'm marking it with a closed circle because we're allowing the equal to. We're allowing it to equal to. And then we have less than 2, so we're going to shade to the left. So this would be the domain using a number line. We want to write the domain in interval notation. That number line is going to help us identify the interval notation. So we're going to have a lower bound. Our lower bound is -infinity, and an upper bound of that shaded region is 2. We use a parenthesis on infinity and a bracket on the 2. The bracket indicates that 2 is included as part of the set. So our domain for this function g of x equals square root of 2 minus x is -infinity to 2 with a bracket on the 2. So for this question, we want to use the graph to determine the domain and range of the function. So we're using the graph to determine that domain and range of the function. And this may be an unusual looking graph to you. It has some features that you may not be familiar with. We've got these dashed lines that are showing up on the picture. And these dashed lines are something that we're going to be learning about in a later chapter, and they are called asymptotes. So let me just explain what's happening on this piece of the graph here. So if we look at this piece of the graph, I'm having a little bit of trouble with my whiteboard. If we look at this piece of the graph here, when we have an arrow on the end of our line, it typically means that the graph continues off of what we're viewing, off of the screen. So typically, if that dashed line wasn't there, we would assume that the arrow just keeps going down and to the left, or sorry, not the arrow, the graph keeps going down and to the left and down to the left and down to the left forever and ever and ever. Well, it does do that. It keeps going down and to the left. However, this dashed line that we see means that it stops at that line. It's never going to pass that line. So it does keep getting closer and closer to that dashed line. So it does keep going down to the left, but it never crosses that dashed line that we see there. The same thing is happening on this side over here. So because we have that dashed line, which is called a horizontal asymptote, the line is continuing the pattern to get closer and closer to y equals 3, but it never gets there. It just keeps getting a tiny bit closer and a tiny bit closer. And then over here, we have those vertical dash lines. Those are vertical asymptotes. And the same thing happens. These lines are getting closer and closer to the dashed line, but never reaching it. And the same thing is happening up here as well. So that's a feature that you may not be familiar with. We are going to study it a little bit more later. But with that in mind, let's find the domain and range of this graph. So when I'm looking for domain and range of a graph, I like to use my ruler. And when I'm finding domain, I hold the ruler vertically. And the reason why I hold it vertically is because it allows me to mark off different places along the x-axis, which is important for domain because the definition of domain is all of the x's. So I'm holding this ruler. You might want to use a pencil vertically. And I'm going to go from left to right. And I'm going from left to right because I'm going to use interval notation. And interval notation always goes smallest to largest, left to right. Okay, so when I am looking for the domain, I'm looking for the first time that my ruler hits the graph. So I can use that as my lower bound, my lowest value in the domain, my lowest x value. And then I'm going to look for when this ruler stops hitting the graph as my highest part of the domain. So let's start doing that here. So because of this arrow that we see here, as I said a moment ago, that means that the pattern continues. This graph continues off screen to continue to move down and left, getting closer and closer to that dashed line. And so that indicates to me that the domain is going to start at -infinity. So as I keep moving to the right, I'm hitting the graph. I continue to hit the graph. And then we reach this dashed line here. So hopefully you remember what I mentioned is that my graph will continue to get closer and closer to that vertical line without ever reaching it. So because it never reaches it, I have a gap in my domain. So my graph does not have an ordered pair with an x value of -2. So that vertical line, that vertical dashed line, is right on -2, and there is no ordered pair on this graph that has an x value of -2. So I'm going to stop my domain at -2, and I'm going to put a parenthesis on -2 because -2 is not part of the graph and it's not part of the domain. However, right after the vertical line, you can see that the graph continues after that vertical dashed line. So my domain starts again. So my domain is going to start back up at -2 and continue until I get to that next vertical line, which is right here at 2. So the same thing happens. This piece of the graph gets closer and closer without ever reaching it. So my domain continues till 2. If I go all along this vertical line, there is no part of the graph. There are no ordered pairs that have an x of 2. So my domain takes a break at 2, but then right after 2, this piece of the graph continues. So from 2 to infinity, I have x values that are part of the graph. So this is my domain. The domain of this graph is from -infinity to -2, union with -2 to 2, union with 2 to infinity. So if we think about this on a number line, we're saying that -2 and +2 are not part of the domain, and every other number on the x-axis is a part of the domain. We found the domain. Now let's find the range. So when we find the range is the set of all y values. We're going to switch our ruler to be held horizontally. Let me erase all my markings here. And I'm holding this ruler horizontally because that's going to mark out different places along my y-axis. And remember, the range are the y's, all of the y's. So I'm going to start at the bottom, that's the lowest y value, and move to the top. So as I look at this, the lowest y value, because of these arrows, meaning the pattern continues, that means that my range will start at -infinity. As I move my ruler up, I'm still touching the graph, and I continue to touch the graph until I get to this spot right here. And this spot has a y value, that ordered pair is 0, 0, has a y value of 0. So my range is going to stop at 0. That point, 0, 0, is part of the graph. It is included in the graph, and 0 will be included in my range. So I'm going to use a bracket on 0 to say that that point is included. We notice that the graph does not touch, the ruler does not touch the graph for this whole section here in the middle. And it's not until we get to this dashed line here that we have some more pieces of the graph. So my range is not going to start again until y equals 3. Now I'm not going to include 3 because this piece of the graph and this piece of the graph are indicating that the line gets closer and closer to a y value of 3 but never reaches it. So 3 is not a point in the range. So we're going to put a parenthesis on the 3. And then as we continue, you can see these arrows at the top, and these pieces of the graph go on forever, and all of the y values are covered. So my range will continue to infinity. So we found the range to be negative infinity to 0, 0 included, union with 3 to infinity. Thank you for checking out my videos. Have a great day.